Okay, so for the last few days, or last couple of days, we've been talking about that exponential growth and equations that look like y equals a to the power of x. You know, we've had 2 to the power of x for doubling and for half-lives and stuff like that. 2 to the power of negative x for half-lives, actually. We've had e to the power of x for other growths. Today we're going to look at the opposite of that, which is a logarithm. You know, we've talked about how every operation we work with has its opposite. You know, addition and subtraction reverse each other. Multiplication and division reverse each other. A power and a root will reverse each other. Well, an exponential and a logarithm will reverse each other. So for a logarithm, let's say that we have, trying to make sure I word this correctly. If I have the exponential y equals a to the power of x, well then that is telling us that log base a of y is equal to x. So you can see here a to the power of x and log base a reverse each other. Let's take the x and y out of it. Log base a of b equals c is telling me that implies a to the power of c equals b. So let's put some numbers in there. Log base 2 is a simple one of 8. Well, that equals 3. The reason is this number, the base of our logarithm, is also the base of our exponent. So that would be 2. This is the actual power then in the exponential. To the third equals 8. Does that make sense? So if I ask you log base 10 of 100,000 equals blank, what that's really asking me is 10 to what power equals 100,000? Well, what power do I have to take 10 to get 100,000? You got it, 5. 10 to the 5th is 100,000. Or if I ask you log base 2 of 16 equals blank. Again, I'm asking you 2 to what power equals 16? What goes in there? Careful. 4. So log base 2 to 16 is 4. Log base 10 of 100,000 is 5. Now there are 2 common bases. Base 10 is used mainly because our numbering system is a base 10 numbering system. So by doing logs, we actually are reducing down our place values to the 1, 2, 3, 4, 5 instead of 10 to the 1, 10 to the 2, 10 to the 3, and so on. And then there is, because it occurs so often in our exponential functions, there's base e. If you just see log, L-O-G, it is implied, if there's nothing here, it's implied to be base 10. Base E actually has a separate notation. They call it ln. That's the log natural or natural log. That's base E. That's why on your calculator the ln key has the e to the x above it. If you look at your log key, there's actually a 10 to the x above it. Those are the inverses of each other. Just like with your, on your trig, you'll have sine and then sine inverse. Sine -1 and sine inverse. So let's take something like 10 to the x equals 548. Now, obviously, this does not come out even. 10 to the second is 100, 10 to the third is 1,000. So how would we solve this? Well, we would undo the 10 here by doing a log base 10. The log base 10 and the 10 to the x cancel each other out. That leaves me with just x. So I have to do a log base 10 on the other side. So you enter log 548 and then hit equals, and it gives you what? 2.738. Very good. We can do the opposite as well. If we have a log base 10 of x equals 7.4. Here we do use the log to get rid of 10 to the power of. Here we got to take 10 to the power of to get rid of the log. So 10 to the power of log base 10 cancels out, gives us just x. Over here it's 10 to the power of 7.4, which is what? $25,118,864.32. So you could actually use that 10 to the x key if you wanted to. You do, the 10 to the second 10 to the x and type in the 7.4 and it'll do it. Or you can just do 10 to the power of, and it works out. But you can see that log and that exponential do cancel each other out. If I have e to the power of x equals 38, and I want to find out what x is, what cancels out e to the power of? ln. So ln and the e cancel out, giving me x. ln of 38? 3.638. Very good. Or the opposite. If I have ln of x equals 2.7, how do I get rid of the ln? E to the power of. You got it. So e and the ln cancel out. I have x here. E to the power of 2.7. Well, that's where you're just going to hit second e, then put in 2.7. 8797.
So when you're calculating to get e, you just hit second ln.
Yep, you've got the ln, so you use second ln, then you type in the 2.7. Well, what if we don't have a base 10 or a base e? What if we have 3 to the power of x equals 80? Well, unfortunately, that won't work out. It's a good idea, but it won't work out. If we have a base in our exponential other than 10 or e, we have to use what's called a change of base formula. So if I want to do log base a of x, all I have available to me are my log base 10 or my log, my ln, my natural log. What I can do is log base 10 of x divided by log base 10 of a. Now let me prove to you that this is going to work. If I have log base 2 of 8, we know that's going to equal 3 because 2 to the power of 3 is 8, right? So that means we're going to do log of 8 divided by log of 2 better give us 3. And it does. Now the neat thing about this is it does not matter whether you use log or ln. I could use ln instead of log if I want to.
So I don't understand how you change the, you just put in, or just write in with that, or?
Well, here's the problem I was given, right? Find the log base 2 of 8. Now we knew the answer was 3, but if we needed the calculator to do it, the base goes on the bottom. This number goes on the top, and then we just use log of each of them. We use log, or we can use ln. So here we use log. We did log of 8 divided by log of 2, it gives us 3.
Oh, okay.
If I use ln of 8 divided by ln of 2, it'll still give us 3. So either one of them will work. So back to this problem here. I have to do a log base 3. Well, the log base 3 and the 3 cancel out. That's just x. I don't even have to calculate anything there. But I have to do a log base 3 of 80. This is going to be log of 80 divided by log of 3. .989. Good. Now there are some, because of our rules of exponents, there are actually some really interesting rules for logs. If I take a log base 2, and I'm going to do 8 times 16 here. And I know I could multiply those out and this would work just fine, but I'm doing this for a reason. What is 8 times 16? Well, 8 times 16 should give us 128. Log base 2 of 128 is 7. Because 2 to the power of 7 is 128. Now remember, if we had to do that, it'd be log of, which one goes on top, the 2 or the 128? 128. The base always goes on bottom. Right? The base of the log always goes on the bottom. So log 128 divided by log of 2 is going to be 7. But we can split this up. Log base 2 of 8 plus log base 2 of 16. What is log base 2 of 8? Well, 2 to what power is 8? 2 to the third power is 8. 2 to what power is 16? Fourth. Which is 7. So here, the rule is log of any base of x times y is equivalent to log of x plus the log of y. So if I have a number that has 2 factors, I can split it up. Why is that handy? So let's do log base 10 of 300. Well, I can split that into log of 100 plus log of 3. Because 300 is 100 times 300. Log of 100, of course, is just 2, because 10 to the 2. Log of 3 is 0.477. So that is 2.477. Well, let's double check it. What is log of 300? 2.477. Now, there's something interesting about logs. We know that log of 100 is 2, right? Log base 10 of 100. Log of 2 is always 0.3 or 0.301 technically, as you can see here. But when you guys are doing your power readings, and we'll talk about those in a couple of days, 0.3 is 2, log of 2. So if I look at this, log of 100 is just 2, 10 to the second. Log of 2 is 0.3, call it 0.301, let's go. So log of 200 is 2.301. If I double that again, log of 400, punch that into your calculator. 2.602, exactly. Why did I know what that was going to be? Well, because that's log of 400 is 100 times 2 times 2, right? So we split that up. Log of 100 plus log of 2 plus another log of 2. Well, this is still 2. This is still 0.301. This is still another 0.301. All I did was increase it by another 0.301. Now, without punching anything in, what do you think you're going to get if I go this up to take this up to log of 800? It doubled again, right? It's going to go up by another 0.301 to 2.903. Because this is 100 times 2 times 2 times 2. So it's just all of this plus another 0.301 for the third 2. So because logs can be split up like that, there's some pretty interesting patterns that develop. For you guys, when you do signal testing, do you guys still have a formal signal testing, or is that in the second year? It's probably in the second year of the program. Okay. When you do signal testing, that 0.3 is a very important. If you're dealing with decibels, 0.3 is very important. If you're dealing with dBmV, decibel millivolts, because the power is voltage squared. It's actually 0.602 or just 0.6 that you look at. A dBmV increase of 0.6 means you've doubled the power. Similar to that, log of x divided by y is log of x minus the log of y. So knowing what we now know, I'm going to do the log of 50 without doing anything on the calculator. Log of 50, of course, can be expressed as log of 100 divided by 2, right? So that's going to be log of 100 minus log of 2. Log of 100 is 2. We know log of 2 is 0.301. This is 1.699. Log of 2, log base 10 of 2 being 0.301. Don't necessarily have to memorize it right now, but in your industry, knowing that is a big deal. There's a lot of companies just say 0.3 and 0.6 instead of 0.301 and 0.602, but the other one that we have, log of x to the power of y, is just y times log of x. Well, what do we mean by that? Well, let's say log of 2 to the power of 5. This is still base 10. Well, that can be just 5 times the log of 2. Since we know the log of 2 is 0.301, that's 5 times 0.301, or 1.505. If I calculate that out, log of 2 to the power of 5, oops, we do get 1.505. So there's all sorts of these rules like this that allow us to combine logs and split them up. And we're going to see examples of things where being able to combine them and split them up is very helpful to us as we go along. Right now, there's some special cases on these logs I want to make sure you see. What is the log of 1? Now think about this for a second. 10 to what power equals 1? 0. Does it even matter what base here? No, because ln of 1 would also be 0, because e to the power of 0 would also be 1. Anything to the power of 0 is 1. So if I'm taking the log of 1, I get 0. Log base 10 of 0.1 is going to be what? -1. Because that's 1/10, or 10 to the power of -1. What if I do log of -2? Gives you an error, doesn't it? We cannot take the log of a negative number. If we have a positive number, there's no power we can raise it to make it negative, right? In fact, log of 0. If I have a positive number like 10 or 2 or anything, what power can I raise it to give me 0? Nothing. So we cannot take log of 0. So when we're taking logs, we have to have a number bigger than 0. It can be 0.00001, but it cannot be 0. So we've got log base x of x. What's that going to equal? Well, what's log of 10? 10 to what power equals 10? 1. ln of e, well, e to what power equals e? 1 here. X to what power equals x? 1. So log of a number that's the same as the base of the log is always going to be 1. Similar, log base x of x to the n. Well, log of 10 to the 5th. Well, 10 to what power equals 10 to the 5th? Kind of self-defining, isn't it? It's 10 to the 5th power. Log base x of x to the n is just going to be n, whatever that power is. If this number equals our base, whatever power it is the result of that log. So I'm going to do log base 10 2,000. Now, without the calculator, how could we figure this out? What can I split 2,000 into? Remember, log base 10, powers of 10 are really easy. 10, 100, 1,000, 10,000. Is there one of those that I can divide out of that? Yeah, 1,000. What would be left? 2. So this gets split up. This is log of 1,000 plus log of 2. What is the log of 1,000? 10 to what power is 1,000? 3, right? 10 to the 3rd power. And we've already established log of 2 is 0.301. Now go ahead and check it on your calculator. Log of 2,000. Perfect. Log of 160,000. Well, I can't really divide out 100,000 here because that'd give me 1.6. So I'm going to divide out 10,000, which would give me what? 16. I know 16, however, factors into 2 times 2 times 2 times 2, right? So what I have here is log of 10,000 plus 4 times the log of 2. That makes sense? Because there's 4 of them. Log of 10,000 has to be what? We're doing log base 10, just count the zeros. There's 4 zeros, so 10 to the 4th, so it's 4, yeah. Plus, this is going to be 4 times 0.301, right? Log base 2 is 0.301. So that is 1.204 plus the 4, 5.204. So again, double check that out. Log of 160,000. 5.204. So there are some useful things here of being able to split those up. Just like if we had log of 5,000. Well, we could do 1,000 times 5, but we don't know the log of 5. So this one would be easier for us to do if we split it up as log of 10,000 divided by 2. Because that's going to be now log of 10,000 plus, minus, multiply, divide, minus, right? Think of it this way. If I had x to the 5th divided by x squared, what do I do to the powers? I subtract them, right? 5 minus 2 gives me 3. Same here. If I've got a log, if I'm dividing two numbers in a log, I end up subtracting the logs of those two numbers. Up here, if I had numbers that I was multiplying, if I had x to the 8th times x to the 7th, I would add the powers to get x to the 15th. Same here. If I have a log of two numbers being multiplied, I add the two logs. So here, log of 10,000 is 4, because that's 10 to the 4th, minus log of 2 is 0.301. So again, that is 3.699. Not so horrible? It'll take a while to get used to. Yeah. It'll definitely take some time to get used to. So we might have this. If I wanted to solve this, I can only get rid of one log. Just like when we had equations, like if we have 5x minus 7 plus 2x equals whatever, I had to combine all my x's together before I could solve that equation, right? Same thing here. I've got to combine my logs. What is, when I add logs, when I'm adding the logs, that's the equivalent of multiplying the numbers. So this is going to be log of 500 times 7, or log of 3,500. I still have minus 2 log 5 is log of 5 squared. When I'm multiplying the log, it's the same as putting a power on that. 5 squared, of course, oops, I should do this. Yep. So this is log of 25. Now subtracting logs means dividing the numbers. So this is log of 3,500 divided by 25. I'm just going back the other way. Instead of taking the numbers and splitting them up into multiple logs, I'm taking multiple logs and squeezing it down to a single log and combining the numbers. So 3,500 divided by 25 is 140. You want me to scroll back up for a little bit? There you go.
I have a question.
Yeah.
Since we know 2 out of 5 is just squaring by 5,
Yep.
couldn't we do it as a subtract just subtract that?
2 log of 5
Yeah.
is log of 25.
Yeah.
Well, at any point we could go ahead and we could, you know, calculate the log of 3,500 and the log of 25 and subtract them. But yeah, you could have done this right away. You could have combined this to get from here to there if you wanted to. You can skip that step. I was just writing it out step by step so you saw how I got from one to the other. I shouldn't have put it equals here because there's no variable there. So we're just going to combine this to get log of 140. And we could calculate the log of 140 if we wanted to. So let's bring that back now to log of 5x squared minus log of x equals 7. But when I combine these two logs, what am I going to do with these elements of the log? I have 3 choices. It's either going to become a power. Well, for it to become a power, it just has to be a number multiplying the log. That's not the case here. I can be multiplying those elements. That would be a plus. This isn't a plus. A subtract means it's divided. So since I'm taking one log minus another log, that means I'm taking the 5x squared divided by x. So this is log of 5x equals 7. I do 10 to the power of, the logs cancel out. 10 to the power of and the log cancels, I got 5x. 10 to the power of 7 is 10 million. I can divide by 5. X equals 2 million. Make any sense? Okay. We're going to have a packet we're going to work out of, and I don't know if it's in the same packet I gave you before or not, or if I got to give you a new one here. Which means 474 through 475. 1 through 75, looking at the odds, what I'd have you do is like every other odd. Do like 1, 5, 9, 13. Yeah, I don't see that you'd have to do 37, 38 problems of this to get it down. If you have to go back and do every odd, that's fine. I mean, it's out there for you to practice. But as I said before, do as many as you need to feel comfortable that you understand how to do them. The biggest thing, let me grab that packet so I can take a peek at it. The biggest thing in that packet is, what is this page? 475. Like doing like 4957 there, being able to split those up. And then also on the backs page here, I guess we stopped at 74, right? 75, okay. Yeah, that's a good place to stop. Tomorrow we'll talk more about 75 through 85, which is using those rules of exponents. So that's a perfect place to stop for now.